Thank you. This is a delightful location. I have been here before, and even though it seems like yesterday, it turns out the last time I was here was in 1990. As I said, it was just yesterday. The work that I'm going to talk about was inspired by conversations I had with Jim Geelen at the University of Waterloo last year. He didn't want to be a joint author of this paper, but many of the ideas in here are his. So I'm going to be talking about extensions of matroids. Okay, so that means I've got a matroid and I want to add elements to it. Now, if the matroid is living inside of a vector space, of course, there are lots of other elements in the vector space that you could add. Those are easy to add, and those are not really the situations that I'm interested in. I'm really more interested in adding elements to matroids which are not representable. Most matroids are not representable, so that's going to be what I'm concerned about. So here's an example. This is a matroid of rank 4. 3 points lying on a line are dependent, so are 4 points in the plane, so are any 5 points. And I'm going to add this element D in red. I've added it on that line ABC. And you can see that when I delete the element D from the matroid M prime, I recover the matroid M. This is an example. M prime is a single element extension of M. I'm just going to call it an extension here. This work was, the foundational work in this area was done by Henry Crapo in 1965. If you know this work, you'll know the term modular cut. And if you've ever tried to do anything with matroid extensions, you'll find that it's not really very simple. Modular cuts are not easy to work with, but matroid extensions turn out to be quite complex. I want to deal with this matroid, the Varmosh matroid. So here it is. This is a rank 4 matroid. You can see various planes there. I've got, if I go around the outside, the non-spanning circuits in this thing, 1, 2, 3, 4, 3, 4, 5, 6, 5, 6, 7, 8, 1, 2, 3, 1, 2, 7, 8, and across the middle, 3, 4, 7, 8. The ends of the thing, 2, 4, 6, 8, and 1, 3, 5, 7 are not circuits, they're not planes. And in particular, the top line 1, 2 and the bottom line 5, 6 are not coplanar, that's a basis. Okay, the question I want to ask is, can I add an element to this matroid that's on the lines through 3, 4 and 7, 8? Now, of course, I can always do that by adding the element as a loop. But that's a trivial extension. I don't want to do that. I want to add it as a rank 1 element. Let's try and do it. Okay, the fundamental rank axiom for matroids is a semi-modularity axiom. Rank of x plus rank of y is greater or equal to the rank of the union plus the rank of the intersection. I'm going to apply that in this situation. So I take the plane 1, 2, 3, 4. I've added the point P on that plane because it's on the line 3, 4. So the rank of 1, 2, 3, 4 P is 3. Likewise, the rank of 5, 6, 7, 8 P is 3. The whole thing's got rank 4. And so that tells me that the rank of 1, 2 P is 2. So I've got a line there through 1, 2 and P. And of course, look at the picture. You can see the symmetry in there. So I've also got a line through 5, 6 and P. But now I've got this situation. I've got two lines meeting in a point, and in particular that means that 1, 2, 5 and 6 are coplanar. That's not a basis. So I can't do this extension. Now in particular this implies that the Varmosh matroid is not representable, because if it were representable there would be a point that I could add on these two lines. So this is a proof that the Varmosh matroid is not representable. But I'm more interested in exactly what this says about representations. So questions about anything I've said so far? Okay. I want to talk about three separations in matroids. So let's go back to the Varmosh matroid. I've got this partition 1, 2, 3, 4, 5, 6, 7, 8. Add the ranks, subtract the rank of the whole thing, you get 2. So this is an example of a three separation. A partition of the ground set, sum of the ranks minus the rank of the whole thing is 2. Some of you might be more comfortable calling this an exact three separation. I'm just going to call it a three separation here. Okay, so back to this picture that I started with. If I look at 1, 2, 3, 4 versus the rest, that's an example of a three separation. Now you could look at these elements A, B and C and you could say, well, okay, there's no reason for them to be on the right-hand side in the separation. They could move. And for example, 1, 2, 3, 4 AB versus 5, 6, 7 C is another example of a three separation. This red line is called the guts line of the three separation. This is what happens when you let Australians do matroid theory, that they introduce this rather lurid terminology. This is not me. This is other Australians that did this. So this is called the guts line of the three separation, and these elements can move. Now, the elements A and B are fixed. Okay, now look at A. You can see that it lies on the line through 1 and 2 and also on the line 6, 7. So it's sort of locked in position. Likewise, B is on the line through 1 and 3 and the plane spanned by 5, 6, 7. It's locked in position. C is not fixed. You can sort of think about C as being able to slide up and down on this line. It's freely placed on the guts line. It turns out to be the only non-fixed element in this matroid. What exactly do I mean by fixed here? Well, I've added the element D. The elements C and D are clones in this matroid. They're independent and they're clones. What do clones mean? Well, if I were to swap the labels on C and D, I wouldn't change the matroid. And I've been able to independently clone the element C by inserting the element D. Suppose that I try to independently clone the element B. Well, that's a fixed element. I can't independently clone it. The only way to clone the element B is to add an element in parallel to it. So that's the difference between fixed and non-fixed. Non-fixed you can independently clone, fixed you can't. Here's a result of Geelen, Gerards and Whittle from 2006, and let's look at the picture here. So I've got a three separation AB, 1, 2, 3, 4 versus 5, 6, 7, and I want to add two elements that form an independent pair of clones, and I want to put them on the guts line of the three separation, and I can do it. The point about placement of these elements is that they're freely placed, and freely placing elements turns out to be easy to do in this situation. You have to define the appropriate modular cut, and then it works out in a simple way. I'm interested in extensions where the elements are not freely placed. I want to define what's called the local connectivity between two sets. So local connectivity between x and y, sum of the ranks minus the rank of their union. Let's look at a matroid that's embedded in a vector space. What's the local connectivity? Take the subspace spanned by x, the subspace spanned by y, take the intersection, and then look at the dimension. That's the local connectivity. So it's really a very useful parameter. Back to this three separation, I want to define what are called strands of this three separation. So here's some examples of what I'm going to call A strands. So A is the set 1, 2, 3, 4. An A strand is a minimal set whose local connectivity with the other side is 1. So 1, 2 is such a strand. So is 1, 4, so is 2, 3. They're not the only ones. 1, 3 is as well. 2, 4 is as well. What about B strands? Well, okay, B is everything apart from 1, 2, 3, 4. And, for example, 5, 7 is a B strand. And so is the element A by itself. That's a B strand. Okay, so here's the situation. I've got 1, 2, 3, 4 versus the rest, and I've got a pair of strands that meet. Look at 1, 4, 5, 7. They sort of meet in the picture, and I can add an element P that lies on this guts line where these strands meet, so that 1, 4P and 5, 7P are circuits. When I put an element in there, you can see that that also forces 2, 3P to be a circuit. Okay, now back to the Varmosh matroid. My three separation, I'm going to colour it red and blue. I've got a pair of red strands, 1, 2 and 3, 4, and a pair of blue strands, 5, 6 and 7, 8. And I've got this local connectivity condition. The local connectivity between a red strand and a blue strand is 1. I would like to add an element, just as I did in the last example, so that 3, 4P is a circuit and 7, 8P is a circuit, but we went through the argument, you can't do that. So what's going on here? What's stopping this from happening? Well, here's the setup. Pair of red strands, a pair of blue strands, and local connectivity of 1 between one red strand and one blue strand. Let's look at the local connectivity between the other pairs of red strands and blue strands. These two other pairs of red strands and blue strands also have local connectivity 1. The problem is, and this is the reason I can't do the extension, is that the last pair has local connectivity 0. So that's the theorem. When you've got a three separation and a pair of strands, so the local connectivity between them is 1, you want to add an element so that A0 union P and B0 union P are both circuits. When can you do it? Exactly what happens in the Varmosh matroid has to be avoided. So you look at the local connectivity. You do not have a second A strand and a second B strand so that the local connectivities are as shown. Exactly 2 of them being 1 and the third one being 0. When you have this extension, it's unique. So the core obstruction to this is encapsulated by the Varmosh matroid. Okay, so the Varmosh matroid is the key obstruction to this extension. I want to add the point P on the line 3, 4 and on the line 7, 8. I recognise that what I'm trying to do is add an element on the guts of a 3 separation, and I can only do that when I don't have 2 other strands, an A strand A1, a B strand B1, so that exactly 2 of these local connectivities are 1. Thank you very much.
Is there any question or comment? Yes.
So if this never happens, I see. So if this never happens, does that guarantee that the matroid's not representable, or can you say anything about representability?
Yeah, that's a good question. I don't know about the answer to the question about representability. One of the things that I have learned about myself over the years is that I can't stand and talk about mathematics and answer questions at the same time. So I'll talk to you about it afterwards.
Is there another question? Yes.
Hi, James.
Sure.
I have this old question. I have this old question about, suppose you take a fluid down in geometry. Can you add a point to it that's not, that's kind of, that's not just free? But I suppose your theorem doesn't really answer that question, because the fluid down in geometry doesn't have free separation.
Exactly.
So,
This is really only the situation that's covered when you've got a 3 separation and you want to add an element on the guts.
okay.
And so it really is encapsulated in the Varmosh.
Any other questions? Okay, if not, let's thank you again.